So in this video, we will look at an example of an event-oriented simulation, developing the logic for that type of simulation. I'm going to assume in this model or in this module that you already have knowledge of event-oriented simulation, and so we're basically starting from the point where you would end in a typical classroom. And so the general process that we follow when we do an event-oriented simulation is first to define the system state representation. As recall, when we do simulation, we're watching a system state evolve over time. And so developing the event-oriented model, the first step is in determining how to represent that system state. Then develop the set of events that cause the system state to change. Determine the processing logic for each of the events. And then once we do that, we actually code the simulation using the system state representation and the processing logic, and then the execution of the simulation just follows the process where we place initial events on the event calendar, we initialize the system simulation time to 0, and then we loop through while we have future events. And the loop that we do is to get the next event from the list, and in this context, next essentially means the next one in simulated time. We update the simulation time to match that next event time. We process the event, and by process the event, we will execute the processing logic that we've defined, and then we exit the loop. And so that's essentially the process that we follow in doing event-oriented simulation, regardless of what we're actually simulating. Meanwhile, the entire time we're executing this loop, we're tracking the statistics during the process. And so we'll start with an example of a driver's license office. And so the process works essentially this way. We're going to assume applicants arrive at the rate of approximately 10 per hour. When an applicant arrives, he or she goes through a check-in process where a single clerk checks the driving history and so on, and gives the applicant the initial paperwork. And we're going to assume that check-in takes approximately 5 minutes. The applicants then take a written exam, and the exam is administered by one of 2 exam clerks. And so if the exam clerks are both busy, the applicant waits until the next one's available. The exam requires approximately 8.8 minutes. And finally, after the exam, the applicants go through a checkout process where they use one of 2 checkout computers and receives his or her temporary license, and the checkout takes approximately 9 minutes. And so note, this is also the example that we use in our first Learning Simio Lab series, where we actually do this same model using Simio. And so in this case, what we're going to do is look at if we wanted to construct this simulation using using event-oriented simulation, how would we do that? And so let's take a look at how we would do that. And so first, what I'm going to do is well, I forgot to mention the performance metrics that we're typically interested in are server utilizations, time in system, and number in system. So we consider these the typical metrics for queuing network type models that we've been focusing on. And so let's look at this in a little bit of detail. And so what I'm going to do is represent the system this way. And so we're going to have arriving applicants, and we're going to have a queue and then a server that will represent the check-in process, followed by a queue and 2 servers that represent the written exam process, and a queue and 2 servers that represent the checkout process. And so our system, when we think about it, can be represented as these 3 basic queuing systems. And we're going to then develop the system state representation, the events, or identify the events, and then develop the event logic based on this paradigm. Okay, so let's think about how we develop the system state. And so to do that, what I'm going to do is I'm going to put some entities in and just assume that there's one person that's being checked in, and there's one person waiting in the queue. There's one person taking the exam, and there are 2 people checking out and 3 people waiting in the queue. And so when we talk about the state representation, what we're trying to do is capture the entities that are in our system and the state of the individual servers. And so our state representation is going to be comprised of the following things. We're going to define in Q1 as the number of entities in Q1, in B1 as the number of units of server 1 that are busy, in Q2 in B2 similarly as the number of entities in Q2 and the number of servers of the number of written exam kiosks that's currently busy, and then in Q3 and in B3. And so when we look at our state represented by the blue dots, we have in Q1 is equal to 1, in B1 is equal to 1, in Q2 is equal to 0, and in B2 is equal to 1, and finally in Q3 is equal to 3, and in B3 is equal to 2. And so our system state representation is these 6 variables, and this is one instance of the system state. And if we think about what would happen if in our queuing system if another entity arrived, so another applicant arrives, what's going to happen is that applicant is going to go to the queue, and in Q1 we'll just go from state 1 to state 2. And so our state vector changes by the addition of one entity or one applicant in Q1. Similarly, if in B1, when this applicant finishes the check-in process, think about what's going to happen. The entity or the applicant is finished here. There's an idle server here, and so this entity will move to here, and in B2 will change from 1 to 2. And then this entity that's waiting in line will move right here, and in Q1 we'll then go to state 1. And so when we think about how the system executes, when we think about simulating the system, essentially what we're doing is we're having events occur and we're keeping track of the changes in the system state when those events occur. Okay, so we have defined the system state representation and gone through a couple of examples of how the system state itself evolves over time. And so the next thing that we want to do is identify the events that occur. And so let me switch slides back here now, and let's think about what happens. And the first thing that we're going to look at is customer arrives. So a customer arrives at time t now. And so the simulation time we're just going to represent using the variable t now, and this is what we're going to call the arrival event. A-R-R-I-V-A-L, this is arrival. And we think about what happens in our queuing system. So the entity arrives, and what's going to happen is the entity is going to look and see, is the server busy? If the server's busy, then the entity is going to get in the queue. Otherwise, the entity is going to start service. And so the pseudocode, the logic that we've used, the event processing logic, is as follows. For the arrival event, we're going to interrogate the busy state. So this is in B1. And if this is equal to 1, then the entity is going to get in the queue. And getting in the queue essentially means we're going to increment the value of NQ1 by 1. Otherwise, else, and so the else would be that NB1 is not equal to 1, which means the server is idle. In this case, what we will do is we will make the server busy. NB1 equals NB1 plus 1. And then we will schedule a future event to occur. So this means that the applicant has started the sign-in process, and at some time in the future, the applicant's going to finish processing. So we will represent that as follows. We're going to schedule a completion event, and I'm going to call it completion 1. COMPL1 is the completion event on the sign-in station, and we schedule this at time t now plus a sample. P-L-E, a sample. Let me see if I can, let me just start that over. Sample. And so what we'll do is we'll sample from some distribution. And we said that the check-in time takes approximately 5 minutes, so this sample might be from an exponential distribution or a uniform distribution, triangular distribution, or some other distribution. But the idea is that we're going to take the current simulation time, sample the processing time, and then we will schedule the event to occur sometime in the future. And so that's all we do when a customer arrives. The customer essentially says, is there room? If the answer is no, in other words, if the server is busy, then the customer gets in the queue. Otherwise, we make the server busy and we immediately schedule a completion event to happen in the future. Okay, so we've completely defined the processing that we do when a customer arrives. The next event that we want to look at is this completion event. So, oops, let me go back here. Didn't mean to do that. This completion event right here. And so when an entity finishes, in other words, if the once the entity starts service on the check-in station, eventually they will finish. And so what happens? Well, the entity is then going to transfer from the check-in to the exam station, and so we can now look at that event. And so now we have the completion event, and we'll also assume this occurs at t now. Now, clearly this won't be the same time as when the entity, the applicant, arrived to the check-in, because some simulated time advances between when they arrived and when they finish, but we're just going to use the variable t now to represent the current simulation time when this event occurs. And so what happens when an entity finishes at the check-in station? It's going to look at the server state, and in this case there are two servers available, and if there's a server available it will begin processing, and if not it will get in the queue. So our pseudocode looks like the following. The first step we're going to do is check the number busy 2, and if that's equal to 2, then the entity will get in the queue as they did before. So we'll just increment NIQ2 by 1. Otherwise, if the number busy 2 is not equal to 2, then at least one of the servers is idle. So we will set that, or increase the number busy. So NB2 will increment by 1. Oops, that's a plus sign, plus 1. So if the value was 0, it will be 1, and if it was 1, it'll now be 2. And then we'll schedule the completion event on the exam. So schedule completion, this time completion 2, at time t now plus sample, where we will sample from the distribution of exam times. Now, in this case, we also have to look at the queue of entities that are potentially waiting. So in this case, when a completion occurs here, what we've done is we've processed the entity that's moving forward in the process, but we also need to consider the entities that might be waiting in the queue for the check-in process. So we will then say if NQ1 is greater than 0, then we need to remove the entity from the queue, NQ1 minus 1, and schedule the completion event on the check-in process. So schedule completion 1 at time t now plus sample. And note, when I say sample in these cases, I mean we're sampling from a distribution, and these will clearly be two different distributions. The one for completion at 2 will be the distribution of processing time at the exam, and sample for completion 1 will be the distribution of processing times at check-in. And if the answer was no, if the number of Q is not greater than 0, then we simply set number busy 1 equals 0. Oops, that's a 1 there, can't get that in. and then close. Well, I have to close the bracket. You can't really see that there. And so we look at our pseudocode and we see what happens when we complete service at station 1. We look at the server state for server 2. If it's busy, we get in the queue right here. Otherwise, we seize one of the servers. In other words, we increment the busy state and we schedule the completion event sometime in the future. Once we process the entity that's moving from server 1 to server 2, we look back in the queue for server 1, and if there's an entity waiting, we pull that entity out. Okay, before we go on, one minor comment here. In the completion 1 event, I had this case where there were no entities waiting in the queue for server 1, and so I set NB1 equal to 0. And this works in this case because this server has single unit capacity. The more general case here, instead of setting NB1 equal to 0, is I want to set NB1 equal to NB1 minus 1. So I just want to subtract 1 from the value. And so that's in essence what would happen if we had a multi-server queue, which you will see that we do in the exam and in the checkout. And so when an entity leaves, we're checking back in the queue, and it might be the case that one of the servers is idle but other ones are busy. And so this representation is more general than the NB1 equals 0. NB1 equals 0 works again in this case because the server has single unit capacity. In the multi-unit capacity case, we want to use the more general notation of NB1 equals NB1 minus 1. So the next event we want to look at is the completion 2 event. So now we've looked at entities that arrive and that complete on 1. Oops, I forgot a 1 here. That's going to be completion 1. And so now we want to look at when entities complete on server 2. And so it's going to look a lot like the logic when they complete on server 1. Instead of moving from 1 to 2, instead they're going to move from 2 to 3. So let's have a look at the code for doing that. So essentially what we're going to do is we're going to say this is completion 2, and we're going to look at the number of servers 3 that are busy, and if that's equal to 2, meaning both of these servers are busy, then we're going to get in the queue. So in Q3 we increment. Otherwise, if we get into the else, that means one of these two, at least one of these two servers is idle. So we are going to increment the number busy. NB3 equals NB3, oops, that's a B3 plus 1, and then schedule the subsequent completion event. So schedule completion 3 at time t now plus sample, where we're sampling the processing time for the checkout process. And just as we did before, we've processed the entity that's going from the exam to checkout, and now we need to look back in the queue and see if there are entities waiting. So if in Q2 is greater than 0, we're going to pull one of them out. In Q1 equals in Q1 minus 1. I'm sorry, that's in Q2 equals in Q2 minus 1. Then we're going to schedule the completion event. Schedule completion 2 at time t now plus sample, and of course the sample again represents sampling from the distribution of processing time at the checkout for completion 3 and for the exam at completion 2. Otherwise, there are no entities waiting in the queue here, so we will set NB2 equals NB2 minus 1. And we see in this case we have to use the more general notation of NB2 equals NB2 minus 1 rather than NB2 equals 0 that we saw before because we have a capacity 2 server. So we've processed entities that arrive, we've processed entities that depart the check-in station, and we've processed entities that depart the exam. Our final event is completion at the checkout. And so This is going to be similar, but not quite the same. And the reason it won't be the same is because the logic here that was associated with transferring the entity from the exam to the checkout, we don't have to use because there's nowhere else for the entity to go. And so our logic for completion 3, get the pen here, completion 3 is as follows. We don't need to check anywhere else because the entities are leaving, so all we really need to do is say, are there entities waiting in the queue? So if NQ3 is greater than 0, then we simply decrement the queue. NQ3 equals NQ3 minus 1 and schedule the completion event. Schedule completion 3 at time t now plus sample. Otherwise, set NB3 equals NB3 minus 1 to indicate that one fewer of the the units of the server is busy. So looking back, if we go back to our initial event, customers arrive, we check the server state, we get in the queue if necessary, otherwise we schedule the completion here. Then on completion of server 1, we move the entity to server 2, and so we check the entity, the server state here, get in the queue if necessary, schedule the completion event if not necessary, and then we also look back in the queue to see if we need to pull one out. Then in server 2, for the completion 2, we do essentially the same thing. We look forward to the queue for the number of busy for server 3, and so on, and then we look back in the queue, and then finally for the checkout station we have nowhere else to go, so the entity just leaves and we don't track it any further. There are no other events we need to deal with, and so we are only looking back at the queue to see if we need to process the entity. And so looking back at our process, what we have done, let me pull all the way back here, is we defined the state representation, which was our 6 components, where we are keeping track of the number busy for each server and the number in each queue. We identified the events. In our case, we had an arrival, we had completion at server 1, we had completion at server 2, and we had completion at server 3. And then associated with each one of these events, we define the logic. And so now the only remaining task, if we were to code this, which we're not going to do in this module, is to actually code these system state representation and the logic, and then place the logic inside this type of loop, where we place an initial event on the event calendar. So in this case, our initial event might be an arrival. So we schedule an arrival to happen at a particular time, and then the process moves forward. Note that the one thing that we didn't discuss at all was this tracking statistics during the process. And as if we go back and look all the way through this, oops, actually we needed to go forward here. What we want to do is track the server utilizations, the time in system, and the number in system. And so clearly these things can be captured in our event logic. We simply would need to modify our subroutines to record these values, and then in the end to go back and do all of the tabulation. And so I think you'll see, if you do an example by hand where you track a set of entities and you track the occurrence of the events by executing the event logic, you'll see how you could incorporate the capturing of all of this information in the code quite easily.